Can you hear me on Zoom?
Yeah.
Perfect. Okay, great. Yeah. Hello, everyone. Shall we get started? Well, welcome in person to CSE 140 Artificial Intelligence. I'm sorry for the weather. I know quite of us have been kind of like soaked. I myself got soaked getting here, so I hope it's going to get better soon. The weather and we're going to be more dry next time. Maybe we'll give a few more minutes until people come, but in general, I will start on time. So yeah, in general, I start on time. If you need at some point to go to the bathroom, that kind of stuff, you can go. You don't have to ask me for permission, but I will start on time. And let's do a quick poll here. So what majors are you all like? Are you mostly like computer science? Like all got it. And so and another question, why do you want to study AI? What's your motivation? Let's hear some answers. Yeah. Just a bit louder so people can hear. So it's a new topic that is popular. Yeah. So it's important in industry to. What are the reasons? Yes.
People everywhere to learn more efficiently, and it'll help create like teaching tools.
Yeah.
That can really help people, and that excites me.
Yeah. So so I'm also streaming on Zoom. So sometimes, yes, like if those people on Zoom cannot hear, I might repeat the question. So
Sure.
So the answer was that it's a very exciting sort of like topic, and I say again, and it helps you to learn, right?
Yeah. To help teach people eventually.
Yeah.
And I think that is really strong for people who don't have access to good education, and that's important.
Yeah. Sounds good. One final question. One final answer. Sorry. Yeah. So you will find it even in museums and in pop culture. That's great. So it is definitely a very hot topic, and it's quite important these days. A lot of people a lot of employers and industry would these days kind of want to computer scientists to know AI, to apply, to know what kind of models to apply, and to build them even from scratch sometimes. So this is what we're going to do in the class this term. We're going to learn how the fundamental concepts about artificial intelligence, how do we build them, and how do we use them on what kind of problems. That's great. Any questions before we start? Any clarifications, questions about the class? Okay. Do interrupt me if you have any questions. There was a question on Zoom actually, whether there was a reading list. I saw earlier, and we may mostly use the textbook. So there won't be, apart from the textbook, there won't be additional reading list. But I will try to point out chapters before each lecture. So here for this lecture, these chapters you see on the white, on the slides, these are the ones that are covering what we're doing today. So when we talk about artificial intelligence, we talk about many things. And in particular, sometimes artificial intelligence is not always the same as machine learning. It's actually, ML is generally a subset of AI, artificial intelligence. Machine learning methods are generally methods that use a lot of data. They're data-driven methods. There's, for example, like supervised learning methods, which are trained on a pairs of inputs and outputs of images. We have unsupervised learning methods, which learn without having any labels at all. Sometimes we have even in-between methods, like semi-supervised methods. There's all kinds of approaches. We have reinforcement learning, which is basically considering an environment, and we take actions in this environment trying to maximize a particular reward. These are all kinds of types of ML methods. So you can find some seats here. Maybe if you come in the front, there's a few seats free in the first row. Anomaly detection sits a bit in the middle. Anomaly detection means these are AI methods that find anomalies in the data, and sometimes I would say these will sit a bit more in the middle. But there's also many other types of approaches which are not generally considered ML, machine learning, and these are, for example, more classical AI methods like rule-based systems, logical inference, expert systems, logic-based reasoning. All of these were generally many types of methods that were developed around the 80s, around the 60s and 80s, and they're still being used even today for example, for like proving theorems and many other kinds of things. For example, even in a computer vision, I've seen papers recently using these kinds of methods. So these are AI, but they're not generally machine learning. They use logical inference and then a knowledge basis as opposed to data. So a few announcements at the beginning of the class. So first of all, the videos and slides are up for first lecture. So I posted I generally try to post the slides at the beginning of the lecture, and even now for the second lecture, I posted the slides beforehand. I converted them to PDFs, so they're not in Keynote anymore, so that everyone can access them. We have already a quiz, which is basically a survey that is due on Friday. So I'll ask you all to fill out that quiz. It's basically a survey. You know, how have you, what kind of courses have you taken in the past, and how related they were to AI, to get an idea of your background. So do that by Friday. The same thing. We also have a worksheet that is also due on Friday, and it's mostly background preparation. These are kinds of like, you know, a few questions on probabilistic kind of like problems, a couple more questions I think on graphs, if I remember correctly. So I think these are things I think you would have done before, so it should be quite easy to fill them up. They are required, but they're not great. They won't count towards a grade, but they are required, so we have to do them by Friday. We have a Python tutorial, like a programming assignment P0, which is a Python tutorial, which is due next week. And it's available. It's actually available on Canvas, not on the web page. So it is on Canvas. Do it. And I'll have office hours. So office hours for both me and also my TAs, they're posted on Canvas. So I'll have my office hours in person in my office on Tuesdays, I think 4 to 6 p.m. My TAs have posted their office hours also on Canvas. So you have them on the Canvas homepage. How many of you are waitlisted students? Got it. And you don't have access to Canvas, right? Yeah, so we're trying to add you also on Canvas, so you can see all of these. As of 4 p.m.
We have added them, right?
You have, oh, they've added them, perfect. I see, I hear in the Zoom. So yes, thank you so much, thank you. Yeah, so you've been added. Yeah, perfect. So that's good. So that's perfect. In that case, everyone has access to Canvas. I'll make announcements. I think so. I was thinking it might be better to make announcements on Canvas instead of emailing you directly. What do you prefer? Would you like me to email you directly like I've done so far, or post on Canvas? Canvas? Okay, I'll do Canvas. Okay, in that case. And also worksheets 1 and problem sets 1 are already available starting today, and they're due in 1 week and 2 weeks. Let me say a few things about these. So worksheets are generally, so they count towards your grade, and they're there to help you do a lot of problem solving. You solve a lot of problems, and you can also try them. You can even redo them a second time, for example. You don't have to be stuck with the one try. The programming assignments, they are more like coding questions, and they're on Pac-Man, on the Pac-Man game. You'll see as you start doing them, and we'll implement a lot of they're super fun. They'll implement a lot of agents and strategies, and we'll have a tournament at the end. The first programming assignment, PA1, it's very long. It's very, very long. So I would recommend you start as soon as possible. And ideally by even a week before the deadline, we recommend you finish the first part of it. So just have a rough idea of a milestone of how, yeah. So do start it as soon as you can. Yeah, and we're gonna clarify. So we'll have to make you some accounts on a server called Sozapol, which is run by Lisa Gitur. So I'm doing that right now, and I will clarify. So we'll make all of you accounts based on a Cruz ID, and we'll give you a random generated password, and you can log in there and run the evaluation of these programming assignments. So I'll get in touch soon with the accounts for all of you to run your evaluation code there. But you can already start reading the assignments, start you download the code base on GitHub and so on. And my TAs will help with that. So the programming assignments, worksheets, ask my TAs on that. In general, with questions, theoretical concepts about the class, about the content, do come to me. But for the assignments, do ask my TAs. How does it sound? Good. Yeah. Any questions? Yeah.
So I could do like the assignments, but how do I know? I'm number one, but how do I know?
Yeah, I know. So I do. Yes, the biggest problem right now, because I would have added all of you on the wait list, is that the room, I'm not allowed to add more because of the room capacity. The room capacity is 100 people, and I'm not officially allowed to. I cannot legally allow more students on the, yeah. So what I would say is, so first of all, let me say this course will be offered again next term in spring, the same course. So you can, even if you don't manage to take it now, it's really not a big deal. You can take it again in next term. It's offered by I think Professor Lani Gilpin. So do sign up for that if you don't manage to get in right now on this one.
Should be my last.
Sorry.
This should be my last.
Your last quarter. Okay. So then. I think a few, well, from my experience, I don't know about this, but from my experience in the past, some students end up dropping the course, and so you might actually get in. But I cannot guarantee. I really cannot guarantee. Yes, I'm sorry. Yeah. Is there anyone else who desperately wants to take the class now and cannot wait for next term? Okay, so one person and 1, 2 there. So maybe we have like 4 in total who desperately want to take it now. Yeah, so what I would recommend. How about we do this? I don't think I can move around students on the wait list. I can reshuffle. I cannot reshuffle the wait list. So what I would say is, if some of you well, who don't plan to take the class, do drop out, so other people, so if some of you like are undecided and think they're kind of like on the edge and might not take it, like do drop out so that other people also can actually join who want to take it. But otherwise, if you're certain you want to take the class, do stay. But otherwise, yeah. How does that sound? Is that good? There's nothing really I can do otherwise. I don't know if it's possible this late to change to a different classroom, because they're all taken and we have to switch to another course. And I don't know if that'll be something that we could do, but I cannot guarantee on that. Yeah. Okay. Yeah. So the programming assignments can also be found on Sozapol, so on the server here. And they also be posted on Canvas. So and again, I said already about logins. We're working on that. Yes, that's what I meant. So if you don't plan to take the class, do remove yourself so that somebody else, like your colleagues, can take it. Okay. So let's talk about uniform search today. Uninformed search. So basically, we have several topics we're going to cover in today's class, and mostly we talk about agents, and then about search strategies for agents and how they search on graphs and in these environments. We'll speak about depth first search, breadth first search, as well as uniform cost search. And finally, at the end, we'll talk about heuristic methods, how we can use heuristics, but actually that we might not have time to cover that, so we might have to do it next time. But that's the plan. So what is an intelligent agent? When we mean an intelligent agent, what is that? So we have an agent that could be like, imagine like a robot, something that lives in an environment and can take actions. So this robot we have can take actions in the environment. And then it also perceives the environment with its sensors. The robot has like a video camera, or it has like a push sensor, or all these kinds of, or LiDAR, or radar, and anything like that. And the agent also has, to be able to take actions, it has these actuators. It's like, like the arms of the robot, or the wheels that help it take actions and move next in the search space. If some of you guys cannot see, you can also move closer in the center if the angle is not great. But this is what we have. We have an agent, which is a robot, and we have an environment, like the world it lives in and takes actions. Everyone with me so far? Yeah. So for example, what are some examples of this? For example, like humans, we are agents. For example, we have sensors, we have eyes, we have ears, and so on. We can taste things. We can perceive the environment at all kinds of levels. And we also have actuators. We have limbs, we have hands, we have feet. We can take all kinds of actions in the environment. We can start running. We can speak. And these are kinds of actions we can take. Like lift a finger, turn left, walk, run, and so on. So basically, the notion of artificial intelligence is the same thing. It's like we take this concept from a human and generalize it to a robot. The robot is the same thing. It has a body. It can take actions in the environment and so on. And this is again a robot. Look at it. It has laser rangefinder. It has some other kinds of sensors like touch sensors and so on. This is how the robot perceives its environment. And in particular for our class, we'll actually use this Pac-Man as an agent. So this will be our little agent and our environment where we're gonna so here you've all seen Pac-Man, I suppose, no? And play this. So the world that Pac-Man lives, this will be the environment, and the agent is our little yellow guy here who's gonna try to find nuggets or food and so on and get a score. And this will be the reward. The score will be the reward, and we're going to try to maximize the score or other kinds of targets depending on what we decide to do. So this is our Pac-Man agents, and so our agent needs to find a path through a maze. It might need to reach a particular location or collect food items and so on, and we can evaluate the agent's performance based on that, based on how many nuggets or food items it gets. So for example, for each action, we can decide that it earns 9 points if the agent collected food. For each, like one food item, 9 points, or it can lose 1 point if no food was collected. This could be a potential reward strategy. And then the goal will be to maximize the score. This will be the goal of the agent. So and this is and now we can introduce the concept of a reflex agent. And a reflex agent is a simple agent that we can say colloquially, it doesn't look ahead into the future too much. The reflex agent just considers the present state as and makes it just in the present state. So it may have some memory of the past, but it generally considers just the present, and then it just acts on how the world is. How many of you remember we spoke a bit about rationality last lecture, right? What was does anyone remember the definition of rationality, how we kind of try to define it? Any ideas? Yeah?
What I wrote down is maximally achieving predefined goals.
Yes.
Decisions, not like thought process.
Yes. So maximally achieving predefined goals. And we also mentioned something also about the utility function, right? And how we can sort of like quantify some kind of like reward with the utility function. So that was the definition of rationality. So sort of like maximally achieving a goal and the utility function. So here the goal is to get as many food items. That this is it's a easy and quantifiable like goal. So that's what a rational agent here would do. We try to eat as many nuggets as it can. Yeah, can a reflex agent be rational? No, it's only looking at the present state. It's not looking ahead into the future. So it's only looking at the present state. So that's why it cannot be rational. But we'll come back to that. So this is an example of a reflex agent. So here is our little guy. So it's following the strategy. It's trying to eat these nuggets. So it's doing quite well. So it's got a score of 599. So the strategy is to collect the closest food item. That's the strategy right now. Just the closest that it has. So that's why it, let's see if I can. So I'm replaying it. Again, the same thing. It starts from here. It just keeps on collecting the closest food item that it can. So I'll just replay it. So what about harder instances? What if we have a slightly harder environment where we have this kind of like wall here, and let's see what it does. So again, it loops around. You see, and it found it managed to eat all of them. Maybe it wasn't the most optimal strategy because it lost a few. Remember, every time it doesn't eat something, it loses 1 point. Maybe you could have done it in a better way, but it worked. We've done this already. So there's also a different type of a class of agents called goal-based agents. So goal-based agents are generally agents that have a goal, like a predefined goal into the future, like they plan ahead into the future. It's like a what if. They try to explore multiple possibilities into the future and try to choose the best one in some sense. So these are kind of goal-based agents. They also must have a model of the world to be able to do this sort of planning. They must have a model of what's going to happen if I take this action. I end up in a new state and then I take another action. So we have to look ahead, maybe 10 steps ahead, 20 steps ahead, and so on. This is, it also would have sort of an evaluation metric to be able to evaluate how good is it if 3 steps ahead, I'm there, I'm in a particular location. How good is that? Is that place to be? Does it make sense? So let's see a goal-based agent. So this, that's a run of a goal-based agent. So you see how it, instead of going down like that, it actually went around, and it's and you see, I think it got a slightly higher score than the previous round. It was 599, if I remember correctly. So this one it got a higher score. So it maximized the predefined the utility. So now we have to talk about, so when we speak about agents that have goals into the future, then we have to, how do they do that? How do they actually reach their goal? So one way to formally define this is basically to solve the search problem. Basically, they have to search into the future and find which are the best actions to take. And a search problem generally, so it's formalized by having a state space. So a state space is a set of all possible states a robot can be. So it's for example here or here, and also the state of food items is also taken into account here. Sometimes there might be no food items here, or there might be just a few. So these are the space of all possible states the robot and the food items can be in. And we also need a successor function. So a successor function basically tells us if we're in a particular state and we take an action, like we go north with this probability of 1, then we're going to end up in this state. This is what the successor function tells us. It tells us if we take an action, go north, where are we going to end up in? Or if we go east, then we're going to end up in a different state. And we also need a start state. So that's the third ingredient. And the fourth ingredient, we need a goal state. But actually, it might be even more than just a single state. That's why we call it a goal test. So a goal test would mean, for example, you stop when you reach a score of 200 or 500. And there could be multiple states which reach that kind of a goal. So that's what we call it a goal test, not a goal state. It could be multiple states that have that predefined goal. So then a solution is a sequence of actions or a plan which transforms the start state into a goal state. So from a start state, we go to a goal state. All good? Yeah. So in the AI literature, the very classical example of doing search spaces was with the cities of Romania. So this was it's actually funny for me. I'm actually from Romania myself, but this is not. I have not chosen this myself. This is an example that has been used in AI literature from the 80s when Russell and Norvig published their book. And the reason why the map of Romania was chosen was because many people in the United States would not be familiar with the cities and the proximity of the cities. So it had to be something that's a map that you didn't know, you have not seen before. So I have seen this map, for example, and I know the cities, but in general, it was intended exactly for somebody who wouldn't know exactly the proximity of the cities. So this is what a robot does essentially when it's in a new environment. They have to start learning from scratch. So that's why. And here in the Romanian example, what's a state space? What do we have as state spaces actually? Yeah.
With the state spaces, be like all the different cities you could be in.
All the different cities you can be in, exactly. That's a state space. Yeah. What about the successor function? What is that in this example? Somebody else. Yeah. The line between each city is a bit more than just the line. There's a yeah. But it's a bit also. It's more like a transition function. It's like if you're in this city, then where you're gonna end up if you go in a particular direction. Yes. So you go to adjacent city with a particular cost. So there's this cost here, yeah, which is 104. So that's what that successor function is. Yeah. But yeah, that was a good answer. What's the start state? Sorry. So this is Arad. So here we have this particular city, Arad, where we start, and the goal test would be to end up in the capital city in Bucharest. So we're starting from Arad, and we have to find a path on the graph which takes us to the capital city. Yeah. So we can formalize it. Is the current state we're in Bucharest? If not, we keep going around up until we find the goal state. Yeah. So what's the solution to this? There's multiple solutions, right? There's multiple paths we can take. 1 second. We can go from here, for example. We can go take this road, or we can take that road. Even this one through Craiova and Pitești and Bucharest, or even through Făgăraș. There's quite a few possibilities. Yeah, there's a question. Have we not been given a condition to minimize the distance? We will have that. We'll do multiple search strategies, and some of them will take into account the weighting, the distance here, and some of them will not. We'll see. The first one will not, and the last one will. There was another question here I saw. Will the solution use Dijkstra's algorithm? It's very related, but we'll see. Yeah. Any other question? So how do we formulate the search problem? How do we formalize it mathematically? So we have to define in general. Oh, sorry. So I'm confused. So this is how about we do a class exercise now? How about we you all take 5 minutes and speak to your neighbor and think of a new problem that would have a new search problem that would and you have to define what is a state space, what is a successor function, and what are the start state and goal test. So it'll take 5 minutes. Talk to your neighbor and write down these, and we'll discuss them afterwards. Yeah. Yeah. You want to make an announcement now, or well after? Let me think. Are you gonna stay till the end of the class? We'll do it now, so you don't, after this. So let's say 5 minutes, and afterwards we'll yeah in 5 minutes. Yeah. Did you were you the one who also emailed me about giving a talk in the AI club? There was somebody. Someone else. No worries. Yeah. Yeah. We give it 1 or 2 more minutes. Yeah. Um, wanna like does it people see my okay,
Is last year? Everyone finished.
Do we have an announcement?
Cohen. Yeah. Hello, everyone. As you guys are all in the artificial intelligence class, assuming you all have an interest in artificial intelligence. Because of that, I kind of want to let everyone know that Santa Cruz has an artificial intelligence club. in this club, we have a wide range of things from workshops ranging from intermediate or intro all the way up to more advanced. Along with that, we have weekly talks from specialists in the field, professors from here, and also outside in the industry. And we have every single quarter, we have a big competition where we're able to earn real money. Last quarter, we had a grand prize of, I think, around $300 for coming up with a machine learning or AI model that follows along with a certain topic. So if you would like to join, we have meetings every week, Tuesday from 6 to 7 p.m. Those will be our workshops. We'll learn different parts of machine learning, with this quarter being a overview of neural networks. And we have meetings also almost every Wednesday, again at 6 to 7 p.m. This one will be online. These are when we have our speaker events. So we'll have, again, different speakers come and talk about what they do and what they like about machine learning and AI. These events that happen on Tuesday will be an E2 180. And we have a Discord for everyone to join. I guess I can send that out some other way. I'll figure out a way to send the Discord for everyone to join. But it's something I suggest everyone join and see if they're interested in, especially since you guys are all here in artificial intelligence class. Thank you.
Thank you. Thank you both. Thank you.
Okay. So I hope those on Zoom can still hear. Yeah, I think so. Let's hear the answers, right? What did we find out? We have a volunteer there. Yeah. The optimal path to take courses so you can graduate in a short amount of time. Yes. So what's the state space there? The classes. Yeah. So the successful function was what's the sequence of classes you have to take to reach the goal state is graduating, and the start state is was again any class that doesn't have a prerequisite. Yeah. Somebody else? What? Any other ideas? Yeah. A Rubik's cube example. Yes. Let's hear that. Great example. Really great example. So again, the states are all the possible states that Rubik's cube can be, and all the faces rotated. The success function is how you turn them, and so on. Yeah. One more example. Let's give one more. Yeah.
And so pretty much the state space would be like the available parking spot. Successor function would be based on the current parking spot, if it's worth it or not to check for a different parking spot. And the start state would be the parking lot entrance, the goal fence would be just, are you at the closest possible parking spot?
Yes, great. So for those who on Zoom who didn't hear, this was an example about parking spots and how and a space over that. Great. So these were all examples we can do. We can basically formulate search problems on, we can search through them. And see. So this is how we're going to formalize them again is with a graph. We're going to have a graph. We'll have nodes and edges. The nodes are the states, and the edges, the arrows. These arrows are the possible successor states that we can follow from the successor function. So, and sometimes it can be hard to build these graphs. Not always it's that easy. Sometimes we'll be using these more like easy examples, but in practice, sometimes it can be quite hard. We can have many states. What are some hard examples where it'll be very hard to express the graph computationally? Yeah.
Social networks.
Social networks.
Data, like a network.
The network.
database of,
Why is it hard there?
just because there's so much variation.
So much variation in what?
Like location, where you are, where you might be, like just database.
Yeah. Some other idea. If something changes, it's dynamic or like what? Yeah. The weather. Yeah. So exactly. So for example, the weather is so we have it's a continuous dynamical process. So I would say that the one keyword is here is continuous. What if we have a process that's continuous, like for example, time, and the weather as it changes over a number of days. So that expressing that time continuously can be quite challenging with these graphs. What if we want to do it every second? We want to update those models every minute. Then we have a lot of data, a lot of states, and not just temporal dimension, but also have like spatial dimension. We express overall. Yeah, it explodes very easily. Say for example, if a robot is moving continuously, that state space is generally quite continuous if it's trying to find a path. So sometimes we have to discretize these things. It might not be easy to discretize it. But okay, so then this brings us to the concept of a search tree. What is a search tree? So we basically express the states. The root node here would be the starting state, and then we take different actions from the root node. We go north with this probability 1, and then from this particular state now we have gone north, or we can go, for example, east, and then we end up in a new state, and so on. And then we expand this further. We take new actions and so on. So this is a search tree. This is what we're going to work with, and we're gonna because you've seen trees so far. I'm sure you've worked with the trees in your previous course in data structure. So we're gonna express as a tree, and we're gonna do search over the tree. Yes, question. So far we're gonna work in a deterministic setting. So that's why we're gonna assume everything is deterministic. So if you go north, you actually end up going north. You won't end up skidding towards the east and so on. So this is a deterministic setting. But in general, some things could be probabilistic. So we'll see if you take CSE 240, for example, CSE 242, machine learning, for example, will do Markov decision processes, and those will be probabilistic. And we also do MDPs here, and we'll see shortly. But we can have probabilistic settings generally, not just deterministic. Question here.
So is each probability separated, or they don't?
Here they're all one. All probabilities are all one. You don't end up you don't have a non-deterministic process. They all probabilities will be one in this example at the beginning. So again, this is another example. This is an example with the Romanian cities. So we started from the city of Arad, and we have to keep expanding the graph up until we reach Bucharest. And the way we're going to do that is by maintaining a fringe node. We'll see very shortly how we do the searches. We're going to maintain a fringe of all the unexplored nodes, and we're going to do either something called breadth first search or depth first search to explore the tree. And I'm sure you've heard of these terms before. And this is what we're gonna introduce, but we're gonna move over those. We're gonna go to some other more advanced concepts shortly. So let's go through the more basic searches first. So this is how it goes. So we start in Arad. We find the fringe. Our fringe are these three cities: Sibiu, Timișoara, and Zerint. We go to Sibiu and expand it afterwards. So we get a new fringe. Now the fringe will be these 4 cities plus these 2 that were still unexplored from before. Our fringe will be all of these unexplored cities, and we keep doing that. So, and this is the general strategy for searching on trees. So this is some pseudocode, but the idea is we initialize the tree using the initial state, and then we keep looping. And then, if there's no candidates for expansion, then we return failure. Otherwise, if we can still expand, we expand the node and add the resulting nodes to the search tree. And but this is more of a general like pseudocode. Don't worry, we'll go to some practical like implementations shortly. And the main question here is which fringe nodes to expand and explore. So which ones we're going to keep having this fringe, but which ones are going to explore. So we see how depth first search and breadth first search are both different choices of how which ones to decide to expand which fringe nodes. So let's consider this graph, this toy graph. It's a very simple graph. We have a start state here, S. We have a goal state, G, and we have different intermediate nodes that we can explore. So, so let's see, how does it work? So, so this is a potential path where we start from S, we go to D, then we go to E, R, F, and G. Yeah. And this is the tree that we were talking about earlier. For this one, we expanded. So we start with the S is our root node, and then we expand to all the adjacent ones. So D, E, and P, which is D, E, and P. So these three ones, and then we keep on expanding. So we can expand D, and so on. We get add B, we add C, and E, and so on. So in general, we see how we construct this tree on demand. As we keep exploring the graph, we'll keep adding more and more in the tree. And a few more observations. So notice how the same node can appear twice. So for example, we have the goal state here, but also here, which means we have different paths that both lead to the goal state. So that's one observation. The second one is that this is a what about cycles? Do we have cycles? What's going to happen with cycles? And this example. Yeah.
Then, like, would it be possible to fully expand it because there would always be more to expand?
Yeah. Yeah, we'll see very shortly. So if we do something in depth first search, we'll be stuck in a loop if we have cycles. Yes. So we'll come back to that. Yeah. But this is you see. So because there's multiple paths, sometimes we see the node multiple times. But sometimes we can actually have cycles, and we can end up essentially expanding this tree forever, and it will have like an infinite depth if we have cycles. So let's review depth first search. So how does depth first search work? So basically we start from the state S. We expand and the fringe, which is D, E, and P, and then we go to the first state and we D, and then we repeat the same process. Then we expand the fringe B, C, and E, and then go to the first one B, and so on. And we keep exploring, and then we go to A, and then we backtrack. Sorry, I missed. So we do that, and then we backtrack, and we do C and then A, and then we backtrack, and then we do the unexplored nodes. So we do E, and then H, and P and Q, and so on. And then we keep doing this, and you can do this at home. You can go to the site at home, and if you're not familiar, but I'm sure many of you have seen this. And we keep doing this up until you find the goal, which was here, and after we find the goal, we stop. We're in with this particular setting, and this is implemented. This is implemented with a type of this called a queue, which is a last in first out. Yeah, so this is a LIFO, means last in first out. This is how we're gonna have data structure to implement this. You have, I think, it's called the queue, right? It's a queue. You put at the last, put new items at the very end, and then you take the first one out to expand. This will also be a queue. Yeah, so this is where we stop at the goal here. We reach the goal and then we stop the search. And even though there was another goal, there was another path here, we just stop at the first one. We don't keep on exploring. So what about breadth first search? So with breadth first search, we do the opposite. We expand we explore the entire fringe first. So if we find the fringe to be D, E, and P, we explore all of these first before we move to the next level. So we go to D, then to E, then to P, and then we explore the entire new fringe next. So B, C, and so on. And then we end up with basically these, let's say, tiers, these search tiers. We'll basically expand go to the first tier, then we go to the second tier, and all through the third tier, and so on. How many of you have seen these? Oh, I see. So I'll go faster then. I'll go faster. But what about time complexity? What about optimality? What about completeness? Let's see about all these properties. Yeah. So what do we mean by what do we mean if that an algorithm is complete? Does anyone know? What's the definition of completeness? Yeah. Guaranteed to find a solution, yes. So complete means that it's guaranteed to find a solution if one exists, yes. What about optimality? Does anyone know or remember? What does it mean for an algorithm to be optimal? Yes. Yeah. So it's guaranteed to find the least cost path to shortest. That's completely correct. So the path with the least cost, the shortest path, all of these are optimality, refer to optimality. Time complexity, space complexity. You're familiar with the notations of like ON notations. Okay. So this is what we mean by time complexity and space complexity. So we'll be using some variables to express these, but we're going to look into these now. So what are each of these properties for these algorithms? You don't have to remember these variables, like and what they map, but we're going to refer to the number of states in the problem, and we're going to express the complexity in terms of that, which is n. The average branching factor b, that our complexities will depend on that. The cost of the least square is the cost of the least or the best solution, and this is c star. So in general, a cost will be c by star with the note like an optimal, the cost of the optimal path. This is what we mean here. S will be the depth of the shallowest solution. And we're also going to be talking about the maximum depth of the search tree, which is the M. So, so for depth first search, is the algorithm complete? Yes, because it can be stuck in a loop. That's why it's not complete. So again, remember, complete is when it finds a solution. So it's not guaranteed to find a solution because it can be stuck in a loop. Is it optimal? No, why? It can search for the first path and not consider another one. Yes, exactly. So it would generally give you, as you've seen here, it will give you the leftmost path. Remember, because it keeps exploring the left branches first. So it'll give you the leftmost path. So that's why it's not optimal. What about time complexity? Yeah, infinity. Yeah. It's at least the worst case is infinity. If you have loops, the worst case complexity is infinity. Space, same for space. So so because of infinite paths, this makes the depth first search like it doesn't have these ideal properties because of that. So how can we fix it? Yeah, you remove a node once you travel to it. Yes. So this is how you in practice, but more in English, what this means is that once we see that we encounter a path which we have explored before, we do not explore it again. So this is what that means in English. So in code in Python, this will be implemented as that. As soon as you see a node, you remove it. So depth first search. So how do we? What about this depth first search now with this path checking? What we just spoke. What about now? What do we have for our completeness? Is it complete now? Yeah. So now it will be complete. Yes. Will it be optimal? Will it find the least cost solution, the shortest path? That was correct. Yes. So no. So you still won't find it. Yes. Even with There was a question there. Does it depend on whether it stops at the first path? It will stop at the first goal it reaches. Yeah, it won't continue. Yeah, as soon as it reaches goal state, even if it would stop there. Yeah.
So when you do the uppercut, you always stop in the queue.
You always stop when the queue is completely, yes. Got it. I get it. So I suppose for here, I know for these slides, we'll flip that definition. We'll see when it reaches the goal state, we'll stop there. I get it that you guys were stopping, had a different stopping criteria, yeah, before. Yeah. It won't change too much. Actually, even if these complexities, well, actually the optimality would change, I guess, if you have it, because you can check the, yeah. That's true. Yeah. The time complexity and space complexity won't change too much. Yeah. So what is the time complexity? So it's exponential. So B is the branching factor, remember, and M is the depth of the how many tiers we explore. So this is, we start from here and we go up to and we stop here. So it's sort of like the depth of the tree, or the maximum depth of the tree. So it's exponential. It's in all B to the power of M plus 1. And space-wise, it's B times M. So it's the branching factor times the maximum depth of the tree. We keep going down. So that's why we have M there, and we multiply by B because every time if we go down a path, we have to keep track of that fringe, and that's why we get to B, which is the branching factor. So that's what we get here. Breadth first search. What about breadth first search? What about it? So is it complete? Yes, it is complete. Is it optimal? No. I put an M with a star. It's a bit more nuanced. When would it be complete? When would it be optimal? Sorry. Yeah. If the graph is unweighted, yes. If the graph is unweighted, or if the weights are all equal, then it will be it will be optimal. But otherwise it won't be. Yeah. What about time complexity? So it's the branching factor, the power of S, where S is the, if I remember correctly, the depth of the solution, where how far away is the solution from the root node. So if it's 3 hops away or 8 hops away. And space complexity, what about space complexity for breadth first search? How much space in memory do we need? So in general, we have to keep track of the fringe, right, of one of these tiers. Like, maybe if you take the maximum fringe, you see here. So at each point, we have to keep track of only the fringe. That's how we expand, and we just cover all of that. So the biggest fringe will be B to the power of M. So that's what I had the B to the M somewhere, and that was correct. Yes. Sorry. Yes. So it's not M. It's S, because the solution would be at level S. But it's Is it all clear? Is there any misunderstandings or clarifications?
So just to confirm,
one sec, we have a question on Zoom. Yeah, go ahead.
So each tier of the tree, that's going to be one fringe.
Each tier of the tree would be one fringe. Yes.
Okay.
It's like So the question was on Zoom. So, and I don't have it. I don't have it on speaker, but it's basically whether each tier would be like a fringe. Yeah. So essentially, when we the fringe would be expanding each tier one by one. So we have see multiple tiers here, and we expand one by one each of them. And the fringe would be the current tier we are currently at, the expanded one. I hope that makes sense. But again, you can ask me in the office hours for more.
Yes. So for DFS, would it just be like the complete branch, like the deep? I guess the deepest that you go.
For depth first search, would it be the complete branch, the deepest that you go? Yes. Yeah. For
Okay.
depth first search, it will be the longest. Yes.
Cool. Thank you.
You're welcome. Okay. I'm sorry you're not hearing the question. It's because if I'm over there, they won't hear me on Zoom, so nobody on Zoom will hear me talking. That's why I have it in the headphone. Okay, so with cycle checking, depth first search is complete. Yeah. So we've done this, we've done these. Let's see a bit of comparisons. Like in general, when will breadth first search outperform depth first search? For what kind of graphs or problems will it outperform? Yeah. With a small graph. Small in what sense? Yes. If the solution is close to where you start, yes. If the solution is close, like it's with a few hops away, then breadth first search would outperform it. It would find it quite quickly. It won't get stuck on a super long branch. What are other ideas? Maybe another scenario, yeah? If it's a complete search tree. Yeah, exactly. If it's more like balanced, yeah. What about when will depth first search outperform breadth first search? Yeah. For a really big graph, breadth first search around memory. Yeah. So breadth first search generally has a higher memory requirement generally. Yeah. Any other question? Any other cases? Yeah. High branching factor. Yes, exactly. That's a very good point. Yes, if it's a high branching factor, then breadth first search will expand too much. Yeah, depth first search will be able to go right in into the branches. Yeah. These are all. So I put some ideas here, but these are all. So I said here, when the solution is not far away from the root node, what our colleague said, when the tree is very deep and solutions are rare, depth first search will take a long time here. So yes, well, breadth first search. So again, depth first search can get stuck if the tree is super deep, like we get stuck at some point, and so on. You can have a look at home, but these are all good ideas. Let me see 1 second. Let me see how we're doing with time. It's 6:50. Oh yeah, we're good. This is So this is the last search strategy we have today. So this one is called iterative deepening, and basically iterative deepening is combining the best of both worlds, combining the depth first search and breadth first search, and sort of like achieving a good balance between the two. What iterative deepening does is that in the first step, you simply do a depth first search only for paths of length 1. And then if you fail to find a solution, you repeat that for paths of length 2. And if you fail, you do length 3 and so on. So you keep doing. So what this means is that you first are at a path of length 1 and you do depth first search on all of these. And then if you're not, you keep on doing depth first search on level 2 and so on. Does it make sense? Yeah. It's kind of similar to that, yes. It is the main advantage. What do you think is the advantage of this as opposed to breadth first search? If you ask the question. Somebody has an idea? Why would you do this? Why? Instead of doing breadth first search, yeah. Yes, less memory usage. So this is the way. If you do it this way, you only do depth first searches like this in like, you know, and this way you use less memory than a breadth first search. Does it make sense? Yeah. It's a bit higher. Yeah, it's a bit higher than both the other two, but it has a balance of with memory. Yes. So it'll be higher than yeah. So that's how we do. So we first do the first level, then the second level, and we do depth first searches here up until second level, then up until third level, and the fourth level up until and then we will find the goal on the fourth level. But because we do only depth first searches, we use less space. So this will be complete. Still, not optimal because of the weights. Only if the weights are equal, it will be optimal. But it will use less space. It will use much less space than a breadth first search. Yeah. Uniform cost. I'm just looking a bit ahead. Yeah, so it's finished, and we have time to finish uniform cost. Yeah. So one final algorithm we wanted to cover today is uniform cost search, and here with this algorithm we take into account the weights of the graph. Remember how we had actually in the remaining example we had distances between cities. We can take this into account. So uniform cost takes these into account, takes the weights into account, all these actions. So now we have a distance of 3 from going from start to D, and so on, and for 1 from here, and let's see how that works. So basically, we start from our start node, and then we have a fringe from start node S0. Then we have a fringe D, E, and P, and we expand the cheapest node first. The cheapest. So here the cheapest would be P, because it has a distance of 1. This is the lowest distance, so we expand that one first. And then we expand, so now we have our new fringe would be D, E, and Q would be the new fringe, and then we expand the cheapest one first, which is this one actually, which has the distance of 3, so D. And we keep doing this, keep expanding the cheapest node, the closest, we can say also, up until we find the goal state. So again, we expand for all of these. You can go to this at home to see the numbers, how they play out. And here we got the goal state, G. And notice how when we do uniform cost search, now we have these contours, these cost contours. This will be like a cost of 0. All these set of nodes that cost 0. This will be the set of nodes at the low cost, and then the green will get higher and higher. So these, for example, these nodes will all be roughly the equal cost away from the source. Yeah. Well, if you want to find the highest cost, I mean, you can simply flip the problem around. You can negate all the costs and then do the lowest cost. If I'm wrong, do let me know. But I think if you just multiply by -1 all the costs, it will still, yeah, it should work. Yeah. So say that again. I did the cheapest, yeah. The cheapest one from the fringe. Is that that was the question, right? If we're taking the cheapest one from the fringe, yeah. we're taking the, so we have a fringe, which are not all at the same level. Sometimes it could be a different depths in the tree, but the fringe would be all a set of nodes unexplored. And we take the cheapest one always. So it's implemented with a priority queue. You have a priority queue, and you always take the first one in the priority queue, the very first node that has the lowest, the highest priority. Yeah. The total weights, like total sum of in the fringe, or in the total, or as we go down the path.
Yeah.
Our colleague already answered. Yes. So to compute these costs for the node, you have to add up all the ones up to there. Yeah. So you have to keep track of that, of the cost up to that point. Yeah. Thank you very much. Yeah. Any other questions? Yeah. If the cost is lower, yes, you will visit the B first. Is that yeah. No, it's always continuous. It has to be continuous because you're always doing a fringe, and the fringe means like you always expand the nodes on the fringe. You don't expand the node outside the fringe. Yeah, it would be You won't. Always from the fringe node. Yes, from the fringe. If you choose outside the fringe, you'll have a break. It's like a discontinuity essentially. Yeah. You always expand from the fringe. Any other questions? Okay. So what about uniform cost search? What about this one? So we have this kind of cost contour like this, which is what we know. And we stop at the first time we reach the goal state. So is it complete? Yes. I'm trying to remember why there was a star there. Why did I put a star? I don't remember. I'm sorry. Yeah. It is. It is greedy. Yes. You always take the yeah. That's exactly right. I see what you mean. Yes, you're correct. Yes. So, although that refers a bit to optimality, right? Because this is like it's a greedy algorithm, which means you might not find a global solution because if you take locally optimal solution, sorry. I have to think about it actually. If it's are you gonna not so talking about optimal? So completeness means if you find a solution. Actually, no, I remember now. Yes, I remember for the start. So it is you might not find a solution if the costs are arbitrarily small. If the costs are arbitrarily small, like kind of like in the limit tending to a zero, you won't. Yeah, there's some like you might not find a solution. You can still get stuck like that. Yeah. Yes. Or also the costs have to be positive. Yes. If the costs are negative, yes, exactly. Yeah, correct. Yes. Now I remember. Yeah. Yes. Okay. This is what it was. Yes. It is optimal, right? Yeah. Yeah, that's what I was thinking about that. This is a greedy algorithm, but I think it actually does find a globally optimal solution because of the properties of the fringe. Yeah. A question here.
How does the cost being of very small affect the completeness?
That's a very good question. I think it's something with like the infinite series of sums, like an infinite series, like you can like if you have a series, like I'm trying to think right now, like I have, yeah, that's a very good question. If we have a cycle, yes, if we keep going through that. Yes, cycle with negative cost, not to keep looping around. Yeah, exactly. Yeah. So here we have, in general, how many tiers we have when we kind of like find the tier where we find, these are now like contours, these kind of cost contours. We'll have around C star divided by epsilon. So C star is like the total cost up until the optimal solution. And we divide by epsilon, which is generally the cost to make one step. And that's how we get like the number of tiers. And the time complexity would be b to the power of C star divided by epsilon. So it's the branching factor to the power of the number of tiers we have in the graph. And the same is the space complexity. Yeah, so what are some issues about this method? So we kind of like, so the key thing is we kind of keep exploring the graph in according to cost, but uniformly in all directions. We keep expanding in all directions uniformly, depending on cost. So we kind of keep getting these, like, so if it's uniform, like uniform cost, we kind of end up doing like this. If it's non-uniform, we get these contours, the uniform in all directions. So again, we don't have like a more directed search, like in a particular direction. So if we have like information about the goal that is in a particular direction, this will be inefficient because it explores in all directions according to cost. But again, the nice thing is it is in general complete and optimal if you don't have those caveats with negative cost. And I think that's it for today. Do we have any questions, general questions? Yeah.
So maybe the next, we're probably going to see how we start at a spot and then ultimately like just go to the goal, like, instead of like switching in every direction. You want to switch to the, is that assuming the next step?
The next step would be to kind of like find to go along the cost contours. Yeah. It's a bit more, no, actually a bit more like doing some heuristics. You'll see next time. We'll do some kind of the way we expand those nodes will be a bit more based on kind of heuristics. We can evaluate the state. We'll see next time. Yeah.
So involves going to a corner and then going back along the same path. So how do we use the given BFS algorithm to solve it? Because the BFS like use a this hidden, right? I mean, I'm using a this hidden, right? So it won't allow it to go back along the same path. But then I can modify the BFS so it works for the corners. But if I do that, it doesn't work for like problem 1 and 2 anymore. So how do I do problem 5, which is do the corners but with BFS?
I don't know off the top of my head, so I have to. So problem 5 is the corner path, which is like there's one path to the corner. You have to go along the same path to get out of the corner. So BFS doesn't let you do that, right? You can't go like back to BFS. So how would you use the BFS algorithm for the problem? You essentially have to use the BFS. it gives you a problem. Like you would use depth first search. With depth first search, with depth.
Yeah, but the problem is specifically use BFS. The BFS algorithm we did it question problem one.
One way. Okay, let me think. I'm thinking off the top of my head right now directly.
So right now, what I do is
you can keep a trace of your, you know, you can come back. You can always come back, and you keep a trace, and you can sort of.
The problem is I tried that, but then the problem is the problem one uses the problem statement, like the default problem statement, and then so can we modify the problem statement? That's like if you can modify the default, like the abstract class problem statement, then I can solve the problem because.
Oh, I think it should. Yeah, it should be. I think with these. Let's see what's the problem with the all the problems with modify those.
Because when we're submitting it says only submit the files you change. So I'm not sure if this it won't work if it's like the process change.
Yeah, no.
Yeah, okay,
Yeah. So like, look, most probably got my TS before. All right. Yeah. What do you mean by the section? Discussion? Because it's just for this course. So actually, I want to have us I will be doing okay. Actually, we will be doing them on some. So my teams will do them on, and they will manage them with office hours. So this way, and they'll go through. They'll send an announcement. And they'll go through to guide you guys through the assignment. But you can join either of them. And they're like optional. It's not like participation fee, but they're strongly recommended to it. And yeah.
Was the reading required or?
It's not required. Again, it's optional, but like yeah. When you do the assignment, what? Vim or what editor? It doesn't matter. You decide. I use Vim myself, but you can use Emacs or something else. It doesn't matter. Yeah, up to you. Yeah, you can use one good one would be to actually try something like a Python IDE, like something like PyCharm. They're quite nice. Yeah, that's something that you could. I would try something like that actually. Yeah.
There's a free tutorial.
Yeah. It's you try to see. Yeah, it's not. It doesn't hurt to learn some of those actually. Yeah, but yeah. All right. What kind of code? Add code. Yeah, I know. I don't have because the classes capacity. They like Leah has not sent me any codes yet. Because I would have been able normally to expand it, but because the room has a capacity limit of 100 people. Maybe wait. Can you take it next in spring? Yeah. So maybe take it in spring. Yes. Mostly, I right now I think it's looking at the low chances that I can get it changed in the room more. That's what I would say. Yeah. Only if you if it's really like urgent, like those people, then we can stay on the wait list. And if somebody drops, then yeah, I think it's looking low chances that I'll be able to change the classroom to this time. Yeah, sorry, yeah.
I was looking at I was thinking about the maximum cost.
Uh-huh.
I don't think making the numbers negative would work. Just because it would be like local maximums. Like if you have 1, 1, 1, and then 1,000, and then it leads to the destination. It's not going to be preferred over 15, 15, 15, 15. It's the destination, right?
Say it again. But what thing are you referring to exactly?
The uniform cost search, but for finding the maximum.
Got it. This one here, right? Like here. Finding you have maximum what? Maximum what?
The largest, the maximum path to G.
You mean the optimal, like the minimal
No,
cost?
max. I was thinking max cost.
Max. Yeah. Max cost. Yes. You cannot flip the signs. You cannot. No.
I guess in this case it would work because you would go down the path 9 first, and then 17, then to 11, and then the ones on the other side wouldn't be considered. But if you had a really large number that would lead, like for example, if
oh, I see. So if you want to find the maximum,
not a great example.
so your question is on something like this: if you want to find the maximum
Yeah, the longest
path.
destination. I can write an example on the.
And again, assuming you don't have cycles, because if you have cycles, you can bump it to infinity.
Yeah.
So I think if you don't have cycles, you could probably well, how about if you expand the maximum node in the fringe, the maximum cost node in the fringe instead of the minimum?
Like you'd go down 9.
Down 9,
right?
and then 17.
Yeah, but then if you had, you'd stop at the first one you found, right? So if you had some, the first node is large, so it would take that path, but then everything else would be small.
Oh, got it.
And then it must be a small cost, and then a very large.
I get
cost
it. I get it. I don't know. Yeah, that's a good question. I don't know. Yeah. Yeah.
You said that you mentioned that PA was like going to be like the longest event. Like, if you want to get like started on this, what would be like the best resource to like get out of it? Just keep doing the readings, or like go to sections and office hours as well.
Second, you want to do? You're asking about the exercises for the PAs.
You said that it's going to be like a 12%, right?
Yeah.
And like
Yeah.
so like just to like get.
Just to get ready.
Mhm.
So do the worksheet, the worksheet and the quiz and the first worksheet as well to get prepared for it. I would say that's enough, and then you just start doing it. Like I would say just start doing it. Like I actually don't think too much about preparing for it.
And also, like I have like trouble accessing the textbook online. Like when I just open the
Yeah.
link online, it just shows the table of content instead of like the actual.
Got it. Yeah, I'll post a link to a PDF version of it. Yeah. I'll update it. Yeah. Yeah. Sorry. Oh, you're driving from Scott Valley? Oh no, a bus, Scott Valley. Yeah. Yeah. So generally, like this is an in-person class. I'm streaming it just in case of like an emergency, like somebody's sick or and so on. You can if you want, but I really wouldn't recommend it. It's actually not worth the network class.
It's just like there's a time issue.
Yeah. Is it on campus? On this campus here?
It is, but it's a little far away, so I have to run.
Right. Honestly, I think that given the trade-off, I think it might still be worth like actually running to come in person. Honestly, because sometimes I might use a Blackboard at some point, like I have used in the past, and I cannot film with the laptop easily on the Blackboard as well and all of that. Yeah.
So, if I email you, sometimes it doesn't just be shared like the Zoom.
Yeah, the Zooming is on Canvas.
Okay.
It's already shared.
So
it's already on no in on the homepage, on the home, on the very beginning.
So in case you find it and
The quiz, I'll do it in class. I was planning to do it in person. Yeah. Yeah, no, I know it's
Yes, you share a link.
yeah, I don't know. I in the sense I can put it on Canvas and then people on Canvas. Yeah, I can do that actually. Yeah, we can do that. I can put it on Canvas. It's gonna start, But in that case, those of you who, so in that case, yes, most people will take it in class, and a few who will take it from Zoom, they'll take it at home. But yeah, I have to think, but it's kind of I want to make sure it's fair for everyone. Like
right.
that's why
Yeah. So is creative like reference? Is it
Sorry.
Is it a more of participation thing, or is it like?
I know. So the quiz will count towards your grade. There's 3 quizzes, and we have 3 modules in the course. At the end of each module, like we'll have a quiz, kind of like everything up to that point. That counts for the grade. We have these class exercises during the class. They used to be used for participation, but actually I won't take participation this time. I won't actually like count participation towards the final grade. But the reason why is because I wanted to do the class exercises with that quiz, the interactive quiz. I'm trading off for that, mostly because that's actually a more interactive tool. We can see live, your answers, and we can compare them. The disadvantage, I cannot track anymore with that, the participation, basically. So I know I can ask you to put names in there, but then I have to go manually through each of them and like count, like, yeah, and they're not linked automatically. Like in Canvas, they would have been linked. Yeah.
Just participation, the quiz.
So the quizzes, yes, they will be graded for correctness. The class exercises.
When you say quiz, do you mean the in-class quizzes or the quizzes on Canvas?
The quizzes on Canvas.
Okay,
Yeah.
yeah.
In class, yeah, I know. I made this mistake last time. I'll rename everything to class exercises. Everything in class will be a CE class exercise.
Okay. So will class exercises be graded?
No.
Okay.
No.
Yeah, I think that was
Yeah. Got it.
The class quiz is not going to be graded.
Yeah. Class exercises.
I think the last guy asked that about the book and I can't open it.
Yeah. I know. I'll put a proper link to the PDF. Yeah.
Thank you so much.
You're welcome. Yeah, good. Oh yeah. Yeah.
How guided will the coding be? Because I took a 144 quarters ago, I believe, which was machine learning, and the professor taught a lot of the concepts and she taught them well. And then everyone really struggled with the coding itself because they didn't.
Which course again? The same course. Machine learning. 144. Yeah. Machine learning. So
And so the coding wasn't. There was a lot of people hadn't really coded a lot with Python and didn't know how to program certain ideas of AI into their work. And so I was just wondering how many will we be guided in any way with our code, or are we supposed to figure out that maybe links to examples or
I would say so. To be honest, I think they're actually quite challenging. Some of those programming assignments, they won't be easy. But I think you have a lot of guidance in those problem sheets, kind of step by step. Even those tutorials and.
Friday. We have one Friday.
The one on Monday would be the programming assignment. That'll be Monday or Tuesday next week. That's due. That'll be programming assignment. And there's a worksheet that's due on Friday and the quiz. So there's 3 things.
And then all of those will help with the.
Yeah.
What would this quiz be?
This first quiz? Oh no, this first quiz is a survey.
Right, okay.
A survey about your background. The worksheet will be about the graphs and stuff. Yeah. The P4. No, actually, no, all the programming assignments, but let me double check. Was it just the final programming assignment or all of them?
What would your policy on group work would be? If I find someone that
for teams of 3, I'll clarify that. Teams of 3. You cannot be alone. You cannot be even in teams of 2. No. Let me double check. I don't remember if for P1 you have to make groups or not.
And then it's not optional to be you'll throw us into a group.
Yeah. It's not optional to be.
Start being able to work with P1.
Right away. Start right away. But let me double check on the groups because I don't remember if the groups are only for P4 or for all the Ps. Yeah. That's Yeah.
If you can't do that
right now.
If you can't, that's okay.
Let me. I'll have to look. Maybe I'll speak to my TAs. Yeah.
Do you want to send email to everyone?
I'll send an email. Yeah. I'll send an email. Yeah. But I know. Feel free to post also on Piazza, all these things
Scared me during the lecture because my name is and you said
really? Yeah. Nice.
That's cool.
Yeah. No.
Very good lecture. I really
Thank
liked the
you.
lecture. It was supposed to be my last quarter,
Yeah.
and this class opened up very last minute. Like all of the operative elections for computer science
Right.
were full, and then they sent an email. This class 140 just opened up, and right away. And I saw you said it's 2 weeks to work on P1. It's it's AI stuff.
You're not on the wait list. You are in the course. Perfect. Yeah.
But I feel like most of the problems I can put in classes where I struggle is when I go to a lecture and I think I'm never going to another one of these.
Yeah.
This is the first one.
Yeah. I'm glad. Yeah. It's the first time I'm teaching the course, so I'm also like figuring some things. Yeah.
That's pretty good.
Yeah.
No, you're a very good lecturer.
Thank you. Yeah.
So,
Yeah.
of all of the DFS, BFS, and then the iterative, I don't know the second word, but
Yeah.
Which one of those would you recommend to use?
I don't know. I haven't looked in depth into on the P1. I scrolled through it. You have to implement a BFS, a DFS. I remember, and ask my TAs. They'll be more familiar. Like I'm figuring a lot of things out because it's the first time I'm teaching it, but I haven't. Yeah, like hopefully by next year I'll manage to do the program myself, but I haven't managed to. Like I didn't have time to implement it yet.
And when it comes to, I assume you've heard of like ChatGPT and GitHub Copilot, maybe.
Yeah.
Out of those things, like let's say you use those to work on assignments. Is that allowed at all? And two, like citing
it. Go ahead and use it. I acknowledge it in the report. Acknowledge it, like all of this. Let me know how it works. Actually, how will it? I'm actually curious. Like how well, because I've tried it a bit, like in the browser to generate some Python code and stuff, and I saw like it was buggy. It generated this some stuff, but it wasn't running properly.
I tried using it for an assignment in C, and it would bug out, and then I did the exact same thing in Python, and it also bugged out, and I mixed and matched the functions it created, and then they both ended up working.
Really?
So that was.
Go ahead and try. We'll talk again later on as things progress. I'm curious if it's actually helpful and in what cases.
Okay, I'll let you know.
Yeah, let me know. Yeah, let me know. Yeah, sounds good. Yeah, you're welcome.
And there's no class Friday, right?
No class Friday. Those Monday and Wednesday. Yeah. You're welcome.
Sorry, can I ask a question quickly about the uniform cost search?
Sure, yeah.
So it'll start out with so at the very beginning, is your fringe just S, node S?
Yes, at the very beginning it's just node S, yes.
And then so what a separate fringe would be considered node P? That'd be the next that'd be the cheapest, right?
Yeah, well at the beginning, so you are at S and then you create a new fringe which is just D, E, and P. That will be your fringe afterwards. So you expand the node, like you expand S and you get 3 more nodes, and that will be the fringe. Those 3.
Okay, so and then from that fringe DEP, you'll find would you essentially create a new fringe from the cheapest node? So like,
no. You from that fringe, then you choose a new node to expand, which is P, which will be P in that case, in here.
Okay, and when you expand it, you just go down like the tiers, I guess.
Yeah, so you add, you expand P, and then you get a new node Q that you add to the fringe. So then your fringe will be D, E, and Q.
Oh, okay. I see what you mean.
And then you from this fringe, from this set of fringe nodes, then you expand the one with the minimal cost, which is 3 now. So then you expand D, because it has a minimum cost.
Okay, and then B, C, and E would be added to the fringe?
Exactly. B, C, and E, these ones will be added to the fringe. Yes. So then the fringe will be B, C, E, this E again, and Q.
Okay.
And
get
these
what
are
you mean.
nodes. The fringe nodes are nodes that you haven't explored yet. So then you haven't explored. You haven't gone to Q yet. You're just in the fringe. It's like you can potentially explore it, but you haven't gone to it yet. You know, Q, E, and yeah.
Okay, that makes sense.
Yeah, that makes sense. You're good. Good.
Yeah. Okay. Thank you. And then just to clarify, there's no class on Monday, right? This upcoming Monday.
There is a class on Monday, no? Or is it? Is it not? No.
Is I think that there's a holiday.
Is it a holiday? Oh gosh, like in that case, let me see. Is it Martin Luther King Jr. Day? Oh, is Martin Luther? Is that an institute? UCSC academic.
I believe so. Yeah, January 16th. Yeah, it's listed as one of the holidays. Yeah, so I guess no class.
Is it an institute holiday? So no class then. I won't have a class if it's an institute holiday. Yeah, I'll announce it then. Oh gosh, why is it? Is this for winter? 23. Yeah, January 16th. Oh yeah. So I won't have a class then on Jan 16th.
Okay, perfect.
Yeah.
Okay, then that was it for my
Yeah,
questions.
I'll announce it. I'll have to announce it. Yeah. Okay.
Okay. Thanks for explaining the uniform search for me.
Yeah. You're welcome. Yeah.
Okay.
Was it easy to hear on Zoom and follow?
Yeah. It was pretty easy to hear it.
I know it's the interactivity is not too great. So that's why I kind of don't recommend generally to attend it from Zoom. But
Yeah.
it's only if you if it's like
Yeah, I'm gonna be traveling, so I'm planning on I guess starting next Wednesday. Yeah, next Wednesday to be back like fully in person.
Yeah.
Okay.
Sounds good. Okay.
Sweet. Thank you so much. Have a good night.
Have a good night. Bye.
Bye-bye.